Okay, now let's take a look at the reversibility. The reversible fuel cell voltage means the voltage generated by the fuel cell in thermodynamic equilibrium. So it means the ideal fuel cell voltage. So you can think that reversible is the same word with the ideal. The ideal fuel cell voltage. So from now on, we will denote the E as the thermodynamically reversible voltage, which means E is ideal voltage, and the V is the operating voltage, which is irreversible. Okay, so irreversible is the same word with real. Okay, so real voltage, and E means ideal voltage. Okay. And heat potential of fuel, it has a relationship between the reaction enthalpy. So reaction enthalpy is related to heat, right? So how can we express the dH? As we learned, dH equals to TdS plus VdP. If we assume that the constant pressure process, then dP goes to 0, so dP is cancelled in this equation, and dH equals to TdS. What is the TdS? TdS is delta Q. So it means the heat of the reaction is the same with the change of the enthalpy in the chemical reaction. Also, the dQ equals to du plus dW. Okay. So the important meaning of this one is that heat of the reaction equals enthalpy change in the chemical reaction. So we call it reaction enthalpy. So the heat enthalpy. Okay. Then how can we calculate the reaction enthalpy? When we see this one, this equation, there is a Moore number of each species. So it is the general form of the chemical reaction, and this one delta HF0 I means enthalpy. Okay, that is the formation, enthalpy of formation in standard state. So this standard state is expressed this form, 0 in the uppercase, and this F means the formation, and this I is the 1 mole of the chemical I species. So this is the formation enthalpy, and how can we calculate it? If there is a product on the right hand, and on the left side there is a reactant. So if you sum up all of the product formation enthalpy like this one, and minus the summation of the formation enthalpy, of reactant. So product, this is the reactant, this is product. So formation of the enthalpy of the products minus the formation enthalpy of the reactant. Okay, that is the reaction enthalpy in the standard. So if you check this example, you can solve the problem related to it in the textbook. And what is the temperature dependence of enthalpy? Okay, and that means enthalpy. Enthalpy and entropy are dependent on the temperature. So let's see the expression. If the formation enthalpy change according to the temperature, we can use the heat capacity to express this one. As I said, this is the in the standard state, right? In the standard state, if we increase or decrease the temperature, how much is the enthalpy changed? So we can express as like this one, and we can derive this one from the dq. Okay, dq is expressed. How can it express this one? Specific heat capacity in the constant pressure process. This is equals to Th, right? Okay, CPdT Th. So if you integral of this small amount of change from the standard temperature to the specific temperature, then we can calculate the enthalpy change depending on the temperature. And similarly, the change in entropy with temperature can be expressed like this. Like this. This is the standard. This is the entropy change in the standard. And if you consider that ds, right, Tds equals to dq, so ds equals to dq over t, and dq equals to dh in the constant pressure, and this is expressed cp dt over t. So if you integral this small amount of change from the T0 to the T, then we can get the delta S. So we can calculate the entropy change like this one. And next, let's move on to work potential of a fuel cell. This part is most important part in the chapter 2. So this is very important. Make a start. Work potential of a fuel cell. Why do we need the fuel cell? To generate electrical work. Okay, so this work means the electrical work. Okay, so what is the meaning of the G? Gibbs free energy means the delta, the change of the Gibbs free energy means the total energy generated by the system. And maximum energy that can be extracted from the system. We call it work potential. So just think that we can consider the Gibbs free energy change is used for work. Used for work we can get. So how can we calculate this Gibbs free energy? As we discussed before, G equals U plus PV minus TS. This is the definition of the Gibbs free energy. And the H in here, H equals to U plus PV. U plus PV. So Gibbs free energy equals to H minus TS. If you differentiate this G, then we can get TH dg equals to TH minus TDS STD. And how about assuming that constant temperature? We call it isothermal process. Then dt cancelled out, goes to 0, and we only have if we express this in the molar equivalent, then we can get this expression, this equation for calculating the Gibbs free energy change. So if we know if we know the amount of the enthalpy change and entropy change, then we can get the delta G in the isothermal process. Okay, so there is an example in the textbook. So just to check by yourself. And let's move on to the relationship between the electrical work and Gibbs free energy. Okay, we can start from G, the definition of G. G equals to U plus PV minus TS, right? Then if we differentiate this one, then we can get this TG equals to du minus ts minus sdt and plus pdv plus vdp. Okay, from now on in the work we can include the mechanical work and electrical work in here. So we can express the work now from now on dp pdv plus dw electric. So if we insert this du into this equation, then the TDS is cancelled and PDV is cancelled out. So there are remaining 3 terms. So the DG equals to minus SDT plus VDP minus, okay, that is very important, minus dw electric. Okay, then now let's assume the important assumption in here. If the T and P is constant, then dt and dp equals to 0. So we can remove these terms, and now we only have one term for expression of the dg. Okay, as I said, dp dt, if the dt and dp equals 0, then dg equals to minus dw electric. And if we derive the equation using molar equivalence, then we can express like this one. The sign of each term is reversed, right? If we have the dg as plus and the sign of the electric is minus, and if we have the sign of the dg as minus and the w electric has the plus sign, right? That is very important factor. So it is effective to assume this condition, right? If we operate the fuel cell, the temperature and pressure is not that fluctuated. That means we can consider the temperature and pressure during the operation maintained constantly. So it is reasonable assumption we can think. And the temperature and pressure remain unchanged during the reaction process, and it is effective at different temperatures and pressure. If we maintain the pressure as 3 bar, then this is also applicable, right? Or 5 bar is okay, but there shouldn't be any other change like this one, right? We should maintain, if we maintain the temperature or the pressure, then we can use this equation. Something like this. It is applicable at each condition. Okay. So what is the meaning of the sign? Then let's check the sign of the delta G. The sign of delta G indicates whether the reaction is spontaneous. Spontaneous means automatically or favorable reaction. So if we have the plus sign for the Gibbs free energy change, then that means the work okay, T work electric have the minus sign because this is plus, and if the Gibbs free energy change has a minus sign, then the electrical work is plus. Okay, then which one is favorable in here? This is favorable, right? Because the electric is plus, right? So we can use the amount of work this Gibbs free energy change. So it means the energetically favorable state. But in this case, if the Gibbs free energy has a plus sign, we can call it as a non-spontaneous reaction, so energetically unfavorable. So if the delta G is greater than 0, that means plus, then the work must be input for a reaction to occur. Okay, so we should find that delta G with a sign of minus, okay, to make a useful work. Okay, useful work. Okay, then how can we relate the Gibbs-Freer change to the voltage, because we want to know about the reversible fuel cell voltage, right? The electrical work is defined as like this. EQ, E times Q. So what is the sign of this one? The sign of this is the volta times Coulomb. This is electrical work. Okay, let's think about it. If we define the P, power, electrical power, how can you define this one? VI, right? P equals to VI. Then what is the unit of the voltage? Volt and ampere, right? And then what is the ampere? Ampere is Coulomb per sec. And the power V times C is Joule per sec. That's why we use the watt unit for expressing the power, right? So remember that VC is Joule, that is work. Okay, so E is the voltage and Q is the charge. And then how can we calculate the Q? Q is calculated as like this one, NF. Then what is N and what is F? N is the number of moles of electrons transferred. And number of moles of electrons transferred. And Faraday constant. What is the Faraday constant? Faraday constant has this value. And what is the unit of it? This is Coulomb per mole of electron. So we can think about it. If there is H2, right? We have H2 and it generates 2H plus proton and 2 electron, right? So what is the number of moles of electron with the 1 mole of the hydrogen gas? Then 2, right? So N is 2 for the hydrogen fuel cell. Okay, let's write on here. Okay, then what is the meaning of the Faraday constant? Faraday constant means if there is a 1 more of the electron in here, then the charge these electrons have is the Faraday constant. This is Faraday constant. So we can calculate the charge and with the NF. If we combine this one, then delta G, which is minus W electric, is equals to minus NFE. Minus NFP. It is really important. Delta G equals minus NFE. And this is the reversible voltage. Okay, then if you find the table in the appendix in the textbook, then we can find that Gibbs-Freer energy change of this reaction, hydrogen oxygen fuel cell reaction. Then you can find this value. You can find minus 237 kilojoule per mole. Okay, so from this Gibbs-Freer energy change, we can calculate the reversible voltage of the fuel cell. So let's assume the product is water in the liquid form. in the standard condition, that is important too. Standard condition, we only talk about the standard until now. And reversal voltage, then we can calculate the reversal voltage like this. If we divide the both side with minus NF, then we can get the reversal voltage in the standard state condition. Okay, if you insert this value in here, and the unit is joule per mole, and N is, as I said, 2, and F is the Faraday constant, then we can get this one. 1.23 volt is the maximum voltage we can get from this reaction. Okay. And also we can find the reversible voltage by using the standard electrode potential. In the table we can find it. So the standard, you can refer to the standard electrode potential table. Okay, and if you sum up of each half cell reaction, then we can get single cell reaction voltage in here. So in the table 2.1 and appendix C, you can refer to this one. Okay, that is the table 2.1, and if we see this one, there should be a criteria, right? So what is the criteria? Criteria is the hydrogen reduction reaction. We set this one as 0. That is the reference. Okay, so hydrogen reduction reaction. The reduction means the electron is accepted in the reactant. Okay, in the table there is the electron on the left side. That means it is the reduction reaction for each species, each chemical reaction. Okay, remember that. And oxidation is the reverse reaction, right? So how can you find the standard hydrogen electrode? Let's take a look at a movie clip.
The SHG consists of platinum wire that is connected to a PT surface in contact with an aqueous solution containing 1 mH plus in equilibrium with H2 gas at a pressure of 1 atmosphere. Let's take a look and see what happens at the standard hydrogen electrode. In this hydrogen electrode, hydrogen gas is bubbled around a platinum electrode. In the molecular view, the PT surface catalyzes the oxidation of hydrogen molecules to protons or the reduction of protons to hydrogen gas. At the electrode, hydrogen gas can either be oxidized to form hydrogen ions or hydrogen ions can be reduced to form hydrogen gas.
Okay, in the single electrode, this oxidation, the blue one, the oxidation can happen, and also in the sulfuric acid solution, the hydrogen ion can be reduced, and so oxidation and reduction reaction can happen in one side.
Hence, two reactions are possible at the electrode. Oxidation. H2 gives 2H plus 2E minus. reduction. 2H plus 2E minus gives H2. This reaction is assigned a standard electrode potential E of 0.00 volt and serves as reference. As you remember, two half cells complete a voltaic cell. Let's take a close look. Here on the left, we have zinc half cell, and on the right, we have standard hydrogen electrode. The electrons are moving from zinc electrode to hydrogen electrode. So, zinc is being oxidized. The voltmeter shows that the standard cell potential of a galvanic cell consists of a SHE and a Zn by Zn2 plus couple is E cell is equal to 0.76 volt. Because the zinc electrode in this cell dissolves spontaneously to form Zn2 plus aqueous ions, while H plus aqueous ions are reduced to H2 at the platinum surface. The standard electrode potential of Zn2 plus by Zn couple is minus 0.76 volt.
Okay, the potential is fixed, is measured through through the experiment, and the specific value is written on this table. So if you can find the chemical species and the reaction, you can refer to this table. And we have an interest on this reaction, the hydrogen and oxygen reduction reaction and hydrogen reduction reaction. And if the reaction is reversed, then we can call it as oxidation, right? Oxidation. Okay, and the last one is reduction. In Korea, this oxidation is 산화 and reduction is 환원. Okay, remember that. And by using this table, let's anticipate which voltage we can get. From the reaction, you can get this reaction. H2 hydrogen gas is oxidized, and the oxygen gas is reduced, right? Oxygen reduction reaction happen, and okay, then we have the electrode potential in here. Okay, in here the hydrogen oxidation reaction is 0, and the oxygen reduction reaction is 1.229, right? 1.229. So we can get the sum. If we sum up of these two half reaction, then we can get the full cell reaction, full cell fuel cell voltage. So based on the stoichiometry, we wrote the 1/2 in here, but in here E0 is not multiplied by this value. Okay, E0 value is independent of the amount of the reacting substance. The voltage is independent of the amount of reactant, right? So one oxidation reaction, one for the reduction reaction. Okay, and this is important. If the smaller electrode potential is reacted in the opposite direction. Okay, if this value is higher, then that is a stronger than the electric potential than other reaction. That means if we compare here, the 1.229 is larger than the 0, right? So this reaction happens in the forward, and this is lower than this one, so the reverse reaction occur. Okay, the reaction means the oxidation, right? The opposite direction. Okay, by using this one, we can calculate the full cell voltage. Then let's take a look at this one, iron and hydrogen ion reaction. If you see this in the table, the iron ion has the electrode potential minus 0.44, and we have the hydrogen ion in here. Then which electrode has higher electrode potential? In here, 0 is larger than the 0.4 minus 0.44, right? So this reaction happens in the forward, and this reaction happens in the reverse direction. Oxidation and reduction happen. So as we anticipate, the hydrogen ion is reduced and the cell voltage is 0, and iron is oxidized, and the potential cell voltage is reversed, as the movie clip explained. And if we sum up this one, we can get the plus 0.44 volt for this reaction. So in here, iron spontaneously becomes oxidized iron ion, and hydrogen gas is generated through this process. This is not battery. Okay, total cell voltage. Okay, and if you apply the external voltage greater than this value, the cell, then this reaction proceeds in the reverse direction. That means the direction of the reaction is reversed, like this one. Okay, because through this applying higher voltage than this one, then this voltage is overcame through this external voltage. Okay, then okay, then let's move on to the next concept and next subject, and calculation of reversible voltage of fuel cell under non-standard condition. Okay, non-standard condition. Until now, we have considered only the standard condition, right? Then standard condition is ambient pressure, ambient room temperature, right? And the concentration is maintained as 1 mole. If we modify these conditions, then what is the effect of this change in the cell voltage, reversible cell voltage? So considering the changes in fuel cell voltage under conditions different from standard condition, what is the variables then? The first one is the temperature, and the second one is the pressure, and third one is activity. That is the same with the concentration of a substance. And from this third part, we will learn about the Nernst equation. It is important in this chapter and next chapter. So thermodynamic tool that can predict the reversible voltage of fuel cells under arbitrary condition. Okay. Firstly, let's take a look effect of the temperature on the reversible voltage. To know that, we have to know about the expression of the Gibbs free energy, because the Gibbs free energy is related to the voltage, right? As we said. And dG equals to minus SDT and plus VdP. Okay. And to know about the temperature dependence, then we should fix the other effect as constant. So we will make a pressure constant. Then dP goes to 0. And if we differentiate with by temperature, then now we can have the minus S. The slope of this the variation is minus S, right? And then if we convert to molar equivalence, then we can express like this. Then let's relate this one to the voltage, reversible voltage. The Gibbs free energy is minus NFE, and we know about the change of this E depending on the temperature. So now we have this one. And then this is the delta, right? The slope of the delta. So ET, this is not a equilibrium room temperature. The temperature is not room temperature. And then this is term for the room temperature, and this is the change, right? So if we multiply the delta T to this slope, then we can know about the delta E. So this is the change of the voltage depending on the temperature. So by using this, we can expect that if the delta S has the positive, then ET has the positive value. Actually, ET minus E0 has a positive value. But if minus, delta S has a minus sign, then this one has a minus sign. The cell voltage will be decreased. So delta is plus, then the ET is directly proportional to the temperature. And if delta has a minus sign, negative, then ET is inversely proportional to the temperature. Okay. So, but when you check the delta S in the fuel cell, delta S has the negative value, then that means the sign of this one has the minus, then the reversible voltage decreases as the temperature increases. That means if we increase the temperature, then the fuel cell voltage will be decreased. Okay. So in the textbook, this is the table, and if we increase the temperature, then the standard potential for this one, get this value and this value too. The potential is linearly decreased. Okay, so let's take a calculation for the amount of decrease. In the hydrogen fuel cell, the delta S of the reaction is in the table. We can find that minus this value, and for the gas, right, the product is in the case of the product of gas form, and if you insert this value into here, delta S, then we can get this one. Okay, and this is the value of the delta T minus T0. So when the temperature of the cell increase by 10 degrees Celsius, 100 degrees Celsius, the voltage of the fuel cell decreases by 12.3 millivolt. It's not that crucial thing, right? Anyway, the important thing is it has a minus sign in here. That is important for here. So, but even though we increase a lot of temperature, but actually the decrease is not that crucial and insignificant. Then how about the pressure effect on the reversible potential? Okay, to know about this one, let's start from this equation, the basic equation, dg equals to minus sdt plus vdp. To know about the pressure effect, we set the temperature as constant, right? Constant temperature, dt equals to 0. And then if we divide the dp on the left and on the right side, then we have v. Wait. Okay, this sign of the here is plus. So if we convert this equation to the molar equivalent expression, then we have this one plus delta V. The volume change, this is the volume, right? Okay, then and also the relationship between the reversible voltage and Gibbs free energy is this one. So the reversible cell voltage expressed when we use it, then we can express the effect of the pressure like this one. In here, the sign of this one, this slope is minus, right? So the change of the reversible cell voltage according to the pressure is related to the change in the volume of the reaction. It is related to the Le Chatelier's principle. If we increase the system pressure, then reversely, the reaction occurs in the direction of the decreasing of the pressure. So the volume of the change of the reaction is the volume change negative, then negative in here, then the voltage increase. And if the volume change is positive, then the voltage will be decreased. So if there is a volume in here, initial and final, then that means the volume change is positive, right? This is positive. Then the voltage is decreased when this happens. Okay, and if the reversely, the the volume of the initial is larger than the final, the product, then it has the negative in the volume change, so the voltage will be increased. Okay. And most of all, the volume change is responsible for from the gas volume change. So we can use the PV equals nRT, ideal gas equation. And by using this one, this V is converted to here, N delta N RT over P in here. In here, so, and in here delta Ng is the change in the total number of molecules, and it is expressed, this is the product, this is for the reactant, right? So this is the Np minus Nr. So if you insert here the pressure as with the temperature, the effect of pressure on reversible voltage is insignificant when you calculate it. I will not calculate it, but actually just calculate by yourself. If the hydrogen pressure is maintained 3 atm, 3 bar, and 5 atm for the oxygen gas, then if you insert the value in here, then we can get the plus 15 millivolt. Okay, and also the temperature and pressure is not that significant, means insignificant, is not important. Okay, anyway, but actually we can quantitatively calculate each effect of the pressure and temperature together. And finally, the chemical potential. The chemical potential explains how the Gibbs free energy changes as the chemistry of the system changes. So this is the chemical potential of I species I in here, in the phase of alpha, liquid or gas. And what is this one? This is moles. Okay, number of the amount of species I. Species of I. Okay, and the Gibbs free energy change. Okay, if the amount of species changes, then how much the Gibbs free energy will be changed. That is the chemical potential. The chemical potential is related to concentration. Okay, concentration, that is very important. Concentration through activity A, and as we did, this is not a standard condition, so this is the standard condition, and additionally we add this RT ln AI. 지금 ln AI is the activity of the species I, and mu I0 is the chemical potential at a standard condition. And what is the activity in here? It depends on the phase or the gas or the pure or not mixed something. So let's take a look at this one. If the species is ideal gas, then the activity means the pressure, partial pressure, And the non-ideal gas, in the non-ideal gas, we multiply this gamma I to reflect the reality, and so this value is between 0 and 1. And for the solution, diluted or ideal solution, the concentration, okay, the concentration is the activity, and the non-ideal solution, real solution, and also we consider this together, gamma I. And in the case of pure substance means pure water, something like that, water, then the activity is considered as 1. This is important for the calculation. Okay, then combining the equations upward and calculate the Gibbs free energy change of the system for chemical I as a sum up of all species, like this one. So if we consider a formula for 1 mole of A, this is 1 mole of A here, then we can calculate the Gibbs free energy change by using this chemical potential and also activity. So the equation is expressed like this. This is the product one, okay? Product 1, and this is also product 1, right? And this is for the reactant. As we did for the product. What is this? No. Reverse. This is the reactant, and this is the product, right? So we can calculate this one. And what is this one? This is the delta G in the standard condition, right? So we have to insert each value in here for the activity. This is not a standard condition, okay? So following the Bantoff isosum, the amount of the change in Gibbs free energy is expressed as a function of an activity of reactant and pressure product, like the pressure and concentration, like that. So this is the Nernst equation. Nernst equation is related to the activity, which is concentration of each species. So the Gibbs free energy is related to the activity, and if we divide the minus NF on the left side, then we can get the E in here, and in here minus NF is divided like this. So this is the general form of the Nernst equation, but we only consider very simple reaction. So just to remember this one, okay, this one. And I think okay, remember that this is the product and this is the reactant, okay? Product, reactant. For the reactant, this is the product. Okay, this is the Nernst equation. So Nernst equation allows reversible changes in electrochemical cell voltage as a function of a material concentration, gas pressure, and others. Okay, Nernst equation is related to material concentration and gas pressure. So if we have this equation, this reaction, then, and let's assume that this generated water is in liquid form. Okay. So if we write down the Nernst equation for this equation, then we can have this one. And in here, the N is the number of electrons from this chemical species. Then the 2 electrons is generated. So N equals to 2. And this is the product part, right? So activity of the water product. And this part is for the reactant, right? Reactant for each one. This comes from minus ln pH2 minus, because this is a half, 1/2 ln PO2. So this one is expressed like this. So the okay. So in the standard condition, the pressure is 1 bar, right? And in here, water, this pure substance, the activity of this one is expressed as 1. So in here is 1. There is 1, and the pressure locate as a numerator, right? So if we insert 1 and 1 to the pH2 and pH2 and PO2, then this terms goes to 0. So that means the reversible potential in the standard condition, right? But not now. So if we assume that 3 atm of the hydrogen and 5 atmospheres of air, then how can we calculate the voltage, reversible voltage? Then insert in here the 3, right? And PO2 in here, because we use the air, so 5 and the 21% is air, is the oxygen in the air, right? So we can insert this value into here. So if you calculate this one, 1.229, then we can get this one, right? And reversible voltage at 1 atm of air is expressed like this. And in the case of the 1 atm of the oxygen, not air, there is only 10 millivolt difference. 10 millivolt difference. So it is not that significant too. But actually, if you change from the air to the oxygen, then in the real experiment, there is a really huge difference. So that is the related to the reaction rate, not this one, not reversible voltage. Okay. Now we just consider about the reversible voltage. Okay. Not related to the reaction rate until now. Okay. And another effect in terms of reaction rate. Okay. Then let's move on to the concentration cell. A concentration cell means a cell composed of 2 electrodes with the same chemical substance of different concentration, and generates voltage due to the different activities of chemical. Difference of this activity activity makes the voltage. And hydrogen concentration cell, in the case of 100 atm in hydrogen fuel compartment, and 10 to the minus 8 atm in vacuum compartment, then they generate this voltage. And okay, let's see the figure in here. So as we calculated before, then we can calculate the E for this one. If there is a electrolyte membrane, okay, and there is a highly concentrated hydrogen gas in this box, in this chamber, and on the other side there is a very highly vacuumed hydrogen inside here, then only they have the same chemical species both, but actually the concentration is different. But what they said is we can make a voltage difference by using the different concentration. So the reversal voltage in this situation, then E0 minus RT over 2F and ln PPPR. Okay, so if you insert each value, okay, R is the 8.314, and room temperature, okay, Kelvin, and F, and the product of the pressure is here, so 100 atm, and I know this is a product, this is reactant, so we can insert the 100 and 10 to the minus 8 atm in here. So if you calculate this one, we can get the value of 0.296 volt. So this is the meaning of the concentration cell and working principle. And then we have the electrochemical potential. Now until now we talked about the chemical potential, but from now on we can consider the electrochemical potential. And this is mu I is the chemical potential, right? This is the chemical potential between them, right? And there is a electropotential, the chemical potential. If we sum up these two, then we can call it the electrochemical potential. What is this one? What is the electropotential? In here, if we don't connect the external current flow electrode in here like this, there is no connection between them, then this plus H plus proton moves through this membrane, and electron cannot move through this one, and they are accumulated in the electrode. So there is a minus charge in here, and the moved proton is accumulated in here, so plus charge in the right side electrode. Then they made the electropotential, right? Electropotential, and this is minus ZIF pi is the electropotential. This is electropotential because of this polarization of it, and this is chemical potential. So this reaction happens until these two values are in equilibrium state. Okay, so this is electrochemical potential, and chemical potential, this is electropotential. Okay. Also, we can, if you see in the textbook related to it, then we can derive the Nernst equation again with based on this assumption. Based on this, not assumption, this is based on this equation, we can derive the Nernst equation. So confirm by yourself in the textbook. And summary, there are three types of the variables, right, which affect in the reversible cell voltage. First, there is a temperature, and temperature change of the slope. The slope of the change is expressed like this one. And there is also pressure. The pressure effect is expressed like this one. But as I said, these values are not that significant. Okay, so but actually for the accurate anticipation, we should consider these two parts. But actually, the third part, the chemical activity, is very important for determining the reversible voltage in the non-standard condition. So the third one is a chemical activity, right? The chemical activity means the chemical composition, concentration, and pressure. And if the temperature is not at the room temperature, then we should change this one. Change this one as ET. Okay. So this is the summary of the effect of the other three variables on the reversible voltage. And finally, in the chapter 2, let's move on to the fuel cell efficiency. So the actual fuel cells are less efficient than ideal fuel cells because of irreversible reaction losses during operation. Ideal efficiency of the fuel cell equals to Gibbs free energy change. That means that, so either reversible fuel cell efficiency can be expressed like this, like a Carnot cycle. We can calculate this one. There is a total energy, right, from the reaction, and what is the useful energy we can get. And as we said, what is the useful energy? Useful work is the change of the Gibbs free energy, and the total energy of the reaction is the enthalpy change. So this is the ideal case, the efficiency in the ideal case, right? And if we compare the Carnot cycle engine efficiency, then we can get this one. This is one might expressed as like this. If there is a TH and there is the thermal engine for generating work, and there is a code TL, and in the Carnot cycle, the engine get the QH, and they generated the amount of the work, and this is expressed as like this one. Okay, this is the maximum efficiency that engine can make. So if we compare these two types of the power source, then the fuel cell has higher efficiency in the low temperature rather than the Carnot cycle, and in the high temperature about 700 degrees Celsius, the Carnot cycle goes over the fuel cell in here about this point, right? And and that's it. Yeah, that's it. This is the efficiency of it. And for the actual fuel cell efficiency, this is somehow important part. And let's take a look at. Firstly, we only talked about the E thermal, epsilon thermal, efficiency in the thermodynamically, right? And there is a two laws too. First one is voltage loss, and the third one is fuel loss. So the actual efficiency is constitute of the multiplying three parts. Okay, three laws. First one, the E thermal. E thermal is expressed as like this one: H delta G over delta H, right? As we said, and the voltage efficiency is expressed. This is the either case. This is the real voltage, right? This is real, and this is ideal. Reversible voltage, right? So fuel cell voltage efficiency, irreversible reaction, the loss operating voltage over reversible voltage. And lastly, there is a fuel utilization efficiency. So current generated by the fuel cell, and total heat supplied expressed in charge rate. Total heat supplied, not this one. Total supplied reactant. Okay, this is not the right one. What I mean is, if there is if there is a fuel cell, and in the anode side or cathode side, if we supply 100 at a rate of 100, and the current is generated at a 50 rate, and the another unreacted gas goes out, right? Unreacted, and this is reactant. This is supply, right? Then, like the second law of the thermodynamics, this all the 100% chemical species cannot be exactly consumed through the reaction. So we consider about this consumption of unreacted flow gas. And okay, this is that one, but how can you express this concept to this equation? This I, what is I? I equals to Coulomb per sec, right? Let's take a look at the unit of it. Coulomb per sec, and N is and is the one more of the H2. Okay, it's very I is a coulomb per sec, and more H2, more electron, and the Faraday constant, the inverse, right? Inverse form there, more electron and the coulomb. Okay? So the unit of this expression is electron. We cancel out the C2. So more H2, the unit of this one, more H2 per sec. So that means the flow rate, right? Flow rate, it is dependent on, it is directly proportional to the flow rate, right? That is a flow rate. But this one is for this one. If we supply the 150 is reacted, this one is the reacted for the reacted gas, and this one means the supplied gas rate, flow rate. Okay, so by using this one we can express epsilon Fourier, and in here epsilon Fourier is expressed as inversely lambda 1 over lambda, and lambda is the stoichiometric ratio SR. So in this case, what is the SR? What is the value of this one? If we want to make a 15, right? 15, then we should supply 100 to react 15, right? Then in here this value epsilon Fourier is expressed 50 over 100. That means 0.5, okay, for half, right? And this stoichiometric is reverse, so it has 2. That means if we want to make 50 reaction, then by multiplying this stoichiometric ratio, we should supply 100. Okay, that is the meaning of the stoichiometric ratio and the efficiency of the actual fuel cell. Okay, that is the end of the chapter 2, and next time let's move on to chapter 3.